to see the propagation of degrees of freedom in a clean way, we move to the Coulomb gauge. Which means that here you have a gauge fixing that instead of being partial mu A mu is this. So we do the same construction. We have minus 1/4 F mu F mu. We keep lambda equals -1, which means that, well, it's the same as here. Basically, instead of having partial, you have del, del, del. This becomes Laplacian, and that's it. So it's exactly the same thing, but these two terms will not simplify, because one has partial and the other one has del. So minus 1/2 squared plus c bar derivative of nabla A respect to A times C. So repeating the calculation, one have minus 1/2 A mu minus box A mu plus 1/2 partial A squared minus 1/2 del nabla A squared plus C bar del C. Well, let's first check the propagator of the ghosts. That will be minus I divided by vector k squared. This does not propagate anything because it doesn't have a pole. There is no on-shell condition that makes it singular. That's why it does not propagate anything. It's not that you have something in the denominator that can become 0. No propagation. This already tells you that the ghosts are out of the picture. Let's see the propagator of the rest. The rest is minus 1/2 A mu in momentum space. Well, what do you have there? Minus box is k squared. Then you have the identity eta mu nu. Then you have plus minus k mu k nu plus nabla tells you that you have eta mu I ki eta nu j kj. You only have the space components. You can write it that way. And now we need to invert that. This we define as q mu nu. And what matrix is this? Let's check. So the Q00 is k squared minus k0, k0, and nothing else, because when mu is 0 or nu is 0, that's 0. What is q0i? 0i, that's nothing. So you have minus k0, ki, okay, ki, plus if this one is 0, you have nothing. Okay. Here you will have k0 minus k, another index, j. And then when you have delta ij, there you have minus k squared ij minus ki kj plus ki kj, because when mu and nu are I and j, this is just plus ki kj. So we have to invert this to find the propagator. We have to invert this matrix. And what will be the form of the inverse? The form of the inverse P mu nu will be something here, something there times k with lower indices. Well, we have to be careful with the indices in the space part. Now we have to use lower indices there. And here there will be some object. You can write two types of objects, eta ij or ki kj. Actually, since I gave them different names here, it's better to use same names. This is D, D, this is B, and this is C. So we multiply that by Q and see what we get. Paying attention to the indices and what is up and down. Well, we can lower those indices and we lose the minus sign. Space indices, so and there too. So here, what is this, by the way? This is just minus space k0 squared. So that simplifies also, because it's k squared, which is k0, k0 minus space. So this is just that. The other one is k0, ki, k0, kj, but we have to use names, proper names for the indices, so now the indices have to be renamed. Let's say that that is in index m. Here we have I, because it has to be I. And so there we have B, eta I, m plus C, ki, km. And we have to find A, B, C, and D in order to get this equal to 1. So let's first multiply this by that and that. So the first row times the first column, that's minus A k squared plus D k0 space k squared. You can collect a space k squared. Yes. Okay. Here I don't have this. I have minus k squared. This k is k. It's not space squared. Delta. Then we first row, second column. That is, there is a km that can be collected. Then you have a k0 minus dk squared. Right? A k0 minus dk squared. See, yes. Then in the other case, you have to multiply this by that and that by that. You will be able to collect a kj minus d space k squared plus bk0 plus c k space squared. The last one, you will be able to collect, well, nothing actually now, because it's d k0 kj km minus, oh, one thing. Yes, this eta is not eta. This eta is a delta. Have to write it delta because eta ij is minus delta. So we have to make a choice. Eta ij are the eta components, so it's minus. So have to make one choice and stick to this, otherwise we get crazy. So this is that minus k squared b delta j m minus k squared c. I'm multiplying these two, kj km. Okay, this should be equal to 1. What does it mean? In particular, this thing should be 0. So, for example, d, or we could say a, should be equal to d k squared to k0, to make that vanish. Another thing that should vanish here should be the coefficient of kj km, because you need a delta, you need 1. And the other coefficient should be equal to 1. So this should be equal to 1, which means that b is equal to minus 1 over k squared. And then there is another condition here. This thing should be 0, which means that d should be equal to minus k squared c over k0. Let's hope the signs are all correct, because we will have a check. So if there is something wrong, we will not get the result. We know that the inverse should exist, so it will exist, but there is a cross-check. Because the fourth condition should be automatically satisfied, but the first condition here we should also have 1, so that is another condition, and then the rest should follow. So let's first combine these three. We remember there are still these two conditions to be used. So that is a k0. So in particular, a is equal to minus c, I guess, because d is equal to that. Yes, b is equal to minus 1 over k squared. Okay, and What about the first thing there? Minus a plus dk0 minus a plus dk0. That should be equal to what? This should be equal to 1 over k space squared minus 1 plus dk0, sorry. And this d, we know that d is equal, well, we can write a in terms of d. A is equal to dk squared divided by k0 plus dk0. So let me collect d divided by k0. That's minus k squared plus k0 squared. You know, you understand where we are getting, because this is d divided by k0, and minus k squared plus k0 squared is space k squared. So we get d. d is equal to k0 divided by k space squared squared. No propagation from here. No pole. A is dk squared divided by k0 is dk squared divided by k0. Let me check.
There is a k squared more in D, in the numerator.
In D?
Yes.
Why?
Because before we written it in round.
So I have this equal to that.
Yes, and then you had another k squared before.
Where?
And the bit before, there's in the up left, you had the k squared. Not left of the matrix.
A is equal to dk squared divided by k0. Don't understand what you're saying. There is a k squared here, but that's c. That's another story. Let's see. Let me check here. A is equal to minus k squared. I have all the signs wrong there, but if they are all wrong, that's correct. Yes, A is that. D is with the wrong sign, but because I'm using a different notation, so probably this is okay. And C is minus k0 d over k squared minus k0 d over k squared. That's hard. That is C. A, B, C. B, we don't have. B is minus 1 over k squared. And now the cross-check is that this object should be identically 0. So C is okay. D has the wrong sign. Yeah, because here I did the multiplication of Q and P instead of P and Q. So let's check. This should be 0. So that's minus D times space k squared plus bk0 plus c, so that's another minus, c k0 squared k squared plus c times that. So the first one has a minus d, then b has a minus and c has a minus. All of them have minuses. B times k0. There is something in c that must be wrong, because c should be even in momenta. So let's check what c is. C is minus k0d divided by k squared. Okay, so c is that. Okay, c is correct. C is correct. Yes, so there is a k0 there that's missing in this multiplication. This times that, okay, this times that, this times that has a k0. Minus k squared space k squared k0. So in the first case you have k squared. Second contribution is plus space k squared. Third contribution is minus k0 squared. The last contribution, yeah, it should be okay, but the last contribution I see has a wrong sign, so there is a wrong sign. Should be that. Here there is a wrong sign because I collected the minus, so first two things are plus and the second one is a minus. Quickly we start checking. So okay, whatever this is, it won't change very much here, so we can start from here. A times that plus d k0 k squared, a k0 km minus k squared, etc., minus d plus b plus c, d plus b plus, and then b, this times that, times that, times that. So a is dk squared divided by k0. B is minus 1 divided by k squared. Okay, let's hope for that. Then you have that D should be no, this is wrong because there is a minus here. I have to put this equal to 0, so D has the wrong sign, which is what gives the correction. D gives the wrong sign. Let's see where we used that. That D is equal to k squared. We only use that for C, so that is enough to produce the right result. Okay, so these are the coefficients A, B, C, and D. You see that only B has a chance to produce anything physical because it has a pole. We can ignore all the other ones. So let's see what the propagator is. P mu nu. No, there is B and C. Also C as 1 over k squared. So you just need to focus on this part, B plus C. So let me collect this factor 1 over k squared. Here there is a 0, here there is a 0, here there is a 0. And you just need b delta ij plus c ki kj. But b is minus 1 over k squared. So maybe I can collect minus 1 over k squared. And c is what? I collect minus 1 over k squared, so I have minus k0 squared over space k squared squared times ki kj. On the pole, that means k squared equals 0. That means k0 squared equals space k squared, which means that these two things cancel out. And so basically you have 0, 0, 0, delta ij minus ki kj divided by space k squared. And if you use k squared equal to k mu equal, as usual, k0, 0, k, then the matrix becomes what? 0, 0, 0, 0, 0, 0, 0. Here you have, for k equal 3, if you put k equal 3 there, this object is 1, because space k is just one component. So you have 0, 0, 0, 0, 0, 1, 1, 0, 0. And those are the two helicities. So the two helicities are the positive residues of the propagators, ghost included, in the Coulomb gauge. You just propagate those two things. It doesn't matter, you don't need to choose a particular frame, but on shell, on the residue, that's all you have. You can rotate it the way you want, but this will always be a symmetric matrix with two positive eigenvalues equal to 1 actually, and 1 0 eigenvalue. If you do the same for gravity, you will find the same thing. And there, we will not do it. In gravity, you find analogous results. In the Brentke gauge. Which means that you consider this gauge condition, instead of having partial mu, you have space part, only space derivatives. And then minus a, you can put a parameter, whatever you want here, delta I mu partial I g rho sigma, the trace basically, eta rho sigma. You can write it for phi if you want, because the derivative g under the derivative is phi, apart from 2k. The derivative of g mu nu is the derivative of the fluctuation around flat space, apart from the constant 2k. We won't do it because it's a little bit long, but the case of QED is sufficient to illustrate what happens, since the physical quantities will not depend on the gauge choice, the most convenient one for to see unitarity, namely that you propagate only the correct degrees of freedom, is the Coulomb gauge. It's not convenient to do calculations because of the form of the propagator and the too many space k in the denominator. You might be familiar with integrals that arise in calculations of loop corrections, and calculating integrals where the denominator doesn't fall off in all directions is much more difficult than with a Lorentz invariant gauge, such as the condition partial mu a mu equals 0, or partial mu a mu as gauge fixing function. So let's illustrate very briefly what quantum field theory is about in a simple case, how you build the scattering amplitudes. We will see the simplest case, which is the 5-4 theory, because every complication that arises with the gauge fields and gravity is a technical complication that once you know how to gauge fix, the theory is not particularly challenging from the conceptual point of view. So this is the Lagrangian, which contains a free part and a simple interaction. And if you work out the free field equations, from the quadratic part, you will have minus 1/2 phi minus box minus m squared phi. And so the propagator here is equal to I times the inverse of that quadratic part in momentum space. Now, to do calculations, and so far we have not introduced any prescription, because unless you do loop calculations, you don't need it. There is a prescription to treat this singularity, which is precisely the on-shell singularity, and that follows from unitarity. Don't know if we have time today to see it, but there is not much else you can do. Let's remember one property of distributions. 1 divided by x minus I epsilon is equal to the principal value of 1 over x plus I pi delta of x. So this plus I epsilon gives a contribution which is precisely the on-shell contribution, because this will be equal to I principal value of 1 divided by k squared minus m squared. And since here we have plus and here we have minus, we have to complex conjugate. There you have minus I pi something on shell. That delta is on shell. And there is not much you can do from unitarity. If you want a particle, that should be non-zero. If you want a physical particle, that should be 1 and not minus 1. Minus 1 in this case and not plus 1. Otherwise, you have negative residues and you violate unitarity. So with this, we will see tomorrow. It's a simple application of unitarity. Unitarity is a statement about the S matrix. SS dagger equals 0, and the S matrix is built by means of Feynman diagrams, which are built by means of this propagator plus a vertex, which describes this interaction. This interaction is phi to the fourth, so it's graphically described by a vertex with 4 legs. And it is equal to a certain constant that's always an I, because you need some minus signs around, which arise by multiplying pairs of i's. And some combinatorics. There is some combinatorics around that we will not mention in detail. But basically, once you have these ingredients, the propagator and the vertex, you build Feynman diagrams, so-called, which are those that give the S matrix after a few steps. For example, this is a Feynman diagram. It's a very simple process that tells you that two scalars, for example, this could be an incoming scalar, and this could be another incoming scalar, so two scalars that exchange another scalar. If you view time like that, time progressing like that. If time progresses like that, you see two scalars that annihilate, give a scalar, and produce other two scalars. This, from this direction, is a typical process at CERN. At CERN, you have two things that collide, produce a Higgs field, for example, and then the Higgs field decays into other things. That's how the Higgs field has been seen, which is not true, because the Higgs field has never been seen. What you see as a process, two things, build something and give something else, and the things they give and the distribution of the probabilities of the events is compatible with the existence of the Higgs in the middle. But we have never seen the Higgs. You cannot see. You cannot see the Higgs, the Z, the W. Many, many things are not seen. So what you see is what is in and what is out. What is inside is protected by the indeterminacy principle. You cannot go there because you would destroy completely the experiment. But in principle, it could be possible to see the Higgs. So let's say the Higgs among the final states, like you see a muon. You can produce a muon and you can see a muon. Although the muon decays after a while, but before it decays, you can see it. The Higgs is so short-living that you just cannot see it. And it's difficult to see it for many other reasons. Anyway, what is this process? You have a vertex here. This is a vertex. So a vertex is minus I lambda. You have a propagator there. Call this momentum P. The propagator is that thing. And then you have another vertex. So you multiply them one by one. And that is a simple Feynman diagram. So the result is minus I lambda squared divided by P squared minus M squared plus I epsilon. What is this P? P is the momentum of this particle that's exchanged. It's not the incoming momentum, it's not any of the incoming momentum, it's an internal momentum. And what you do, normally you build Feynman diagrams, but you do not put propagators on the external legs. So they are called amputated Feynman diagrams. What would you get if you put propagators on the external legs? That's a non-amputated. Well, that is equal. Here you will have a momentum P1, here you will have a momentum P2. P will be the sum or the difference. P is equal to minus P1 minus P2. Okay. Or it is P3 plus P4. By the conservation of momentum. Well, basically it is a bunch of propagators times the amputated diagram. So you put the propagators of everything, whatever the particles are outside, probably they are all different. So you see, when you have a non-amputated diagram, you have a multiple pole. All the propagators outside are poles, and on shell you have a residue. The amplitude is a residue of a multiple pole. All amplitudes are residues of multiple poles. And because in perturbation theories the external legs are free, you just jump to the residue by ignoring the propagators on the external fields, which means on the external legs, which means to amputate the diagram. So when you amputate the diagram, you are automatically computing the residue that you are interested in, which is the residue of a multiple pole and the number of zeros tell you which particles you are scattering. So here there are zeros of this kind, so you are scattering those 4 particles. And in perturbation theory, these are just the external legs. So in perturbation theory, you know what you are scattering by looking at the external legs. It's not like that in a non-perturbative theory like QCD that generates hadrons out of quarks. That's a much more difficult problem, but in perturbation theory you just amputate the diagrams and you get what is the amplitude. So tomorrow we will apply the unitarity equation to this diagram to check the meaning that this plus I epsilon must be there precisely with this sign and this coefficient.